Hopefully you've seen my video of how you can make your own ink blot photometer. All it requires is a 3x5 note card, really any piece of paper, and some cooking oil. And if you smear a circular blob of cooking oil onto the index card, it'll make a stain, and depending on how the note card is lit up, that ink stain will look brighter than the card or darker than the card. So for example, if you're looking from the right side and the left side is lit up with a bright bulb, then the card is going to look dark and the oil spot's going to look bright. However, if you switch it and move the light bulb to the same side that you're viewing from, then it's the opposite effect. The oil spot looks really dark and the rest of the card looks really bright. So one experiment you could try would be to take two light bulbs of equal intensity, maybe a 60-watt bulb and another 60-watt bulb, separate them by any distance you want, and try to find out where you would have to put the photometer so that you don't notice any difference in the brightness of the card itself versus the brightness of the oil stain. So, well, it turns out if they're equal power bulbs, then to get the intensity number 1 and intensity number 2 on both sides to be equal, you just have to adjust until the brightness of the stain and the brightness of the card are one and the same, and that's going to be right at the midpoint. So if the two bulbs are separated by a distance d, then this distance is guaranteed to be d over 2. Now what if you change it? What if this becomes a 100-watt bulb and the other one still stays 60 watts? Then what do you think you'd have to do? Yeah, you're probably going to have to move this card farther over here so that it appears to be equal intensity on both sides. So then if this distance right here is, well, we'll call this one D, we'll call this one capital L, then I guess this distance becomes L minus D. In any case, then you can verify that the power of bulb number 1 divided by 4 pi times L minus D quantity squared equals the power of bulb number 2 divided by 4 pi times d squared. The reason for the 4 pi and d squared, the surface area of a sphere is 4 pi r squared. And so I'm just imagining a sphere concentric with bulb number 2 and all of its power radiating equally in all directions through that sphere. And then because you're farther from the brighter bulb, that's a sphere with a bigger radius, and so its surface area is larger. So the surface area that the light passes through from bulb number 1 is 4 pi times L minus D squared, and the surface area of the red sphere is 4 pi times D squared. So intensity is power over surface area. So here we're setting the intensities equal. The 4 pi cancels out, and then it would just work out that the ratio of the power of bulb 1 divided by the power of bulb 2 is the same as the ratio of L minus D quantity squared over D squared. So here's where the experiment gets interesting. Instead of using a 100-watt bulb as the brighter bulb compared to the 60-watt, what if you kept the 60-watt bulb and you let the other bulb be the sun? Then the experiment, you'd find that you have to hold the index card very close to the light bulb. So when you view it, it appears that the intensity from the sun and the intensity from the bulb are equal. All you need to do is measure this distance, d. Now this distance between the sun and the note card, you can't measure it, but you know it. It's just 1 astronomical unit, or 1.5 times 10 to the 11th meters. So for intensity from the sun to equal the intensity from the bulb, the power from the sun divided by 4 pi r squared has to equal the power rating of the bulb divided by 4 pi d squared. Again, we'd cancel out the 4 pi, and so we would find the power of the sun is 1 astronomical unit divided by the distance, all quantity squared, multiplied by the power of the bulb. So let's say you tried this experimentally and you found that this distance is about 6 centimeters. That would mean the power of the sun would be 1.5 times 10 to the 11th meters divided by 0.06 meters, quantity squared, all multiplied by 60 watts. And that comes out to 3.75 times 10 to the 26 watts, and that indeed is very nearly the power of the sun. Now, I made this number up. I didn't actually do the experiment and measure it, but I think I would find that the distance would probably be something a little greater than 6 centimeters when I try it. So my answer would probably come out to be something less than 3.75 times 10 to the 26, but I'd actually only expect to get a result of 3.8 times 10 to the 26 watts if I lived at the equator and I tried this experiment at noon when the sun is directly overhead and I align my light bulb and the sun directly along the same line. So the fact that we live at higher latitudes means we don't expect to see that power rating because the intensity of sunlight we get is not the same as the intensity that you would get at the equator. So I encourage you to try this experiment yourself. Very easy. All you need is a ruler, a light bulb, an index card, and some oil, and you can calculate the result.